So we can continue and maybe finish today this elementary topic about computer arithmetic. Which is about how you represent numbers and perform elementary operations. So just something very, very basic for numerical analysis, but important. So we already said that we use these floating point numbers. Which means that the number, you always put point after zero, after the last zero. So 0, and then B1, B2, B3, and so on. So this is how we represent a number, which must have finite number of digits, and it's multiplied by certain power. So in this structure, we have a base, beta, which is, in most cases, it's either 2 with a binary decimal that we used to its 10, and there is also 16 also used in numerical analysis. And then there is plus or minus in front, so we have a m is exponent, and the other part is this number is a mantis. Okay, so this is how all the numbers are represented, and t is the number of digits that. So this is the number of digits in your arithmetic. Digits. So that's an important property. So I already mentioned that there are the fact that there is a finite number of digits. So it's actually discrete approximation of real numbers that automatically mean that there can be a huge number of problems that are caused by the fact that it's not precise. So there was one. I gave you some very simple examples. So I think it's good I give you one more example. So then this is example. Which it has to do with this Gauss elimination method that we was talking from the very beginning, so Gauss elimination. Method, which is a simple method of solving linear equations. And what we do is we try to solve the system where it will be minus 0.00, how many 4 zeros? No, 3 zeros enough. 1 x1 plus x2 equal 1, and 0.5 x1 plus 0.5 x2 equal 1. So let's solve this system. So remember how you solve this system exactly with the Gauss elimination method. So what you do, you take a combination. So essentially what you can do is you can, let's do it like this. Just remove this 1/2, b plus x2. Also be 2, like this, just short. Okay, so what you do is you eliminate x1. So let's eliminate this x1. So what you do, you take second equation, and plus you have to multiply it by 10,000 by the first equation, and then you substitute, put it in the place of the new equation at the second position. So when you multiply it by 10,000, the first component will vanish, so the resulting system will be like this. So the first equation remains. And the second equation so what happens? So first we'll cancel, and then in the second position you will have 10,001, right? X2 equal 10,002. Yes. Correct. And then by back substitution, you solve the problem. So you find that, switch it off. So you find first x2 from the last equation. It will be 10,002 divided by 10,001. So this is something very close to 1. And then you back substitute this value here. And then you find that x1 is, so it will be 10,000 by, with a minus, no, with a plus. 1004 x2 minus 1. Yes. So this is more or less okay. That 10 powers 4. Like this, no? Oh no. X2, X1 is 2 minus 1. And then this is what? So just subtract 1 from here. It will be 10,000 by 10,001. So it's also very close to 1. So there is a very clear result of the system which both of them are very close to 1. So now make it a digital computation. So use floating point arithmetic and try to do exactly the same operations, but we know that that we now have only finite number of digits, right? So whenever we have finite number of digits, so we will be on our usual decimal base, and let's say how many digits? 3 digits. We keep 3 digits. In realistic situations, we keep 16 digits, but you can have just the same situation, but in a more complex problem, as we will see now. So 3 digits. So how everything will work? So first of all, equation will be written in a standard form. So it will be minus 0.1. So it's 10 minus 3 x1 plus 0.110 x2 equal 0.110. So this is how the computer will see it. And then here we have same thing, 0.1. Okay. So and then whenever you do the operation, so you come to the second equation. So after you're doing exactly the same operation, the first equation will remain the same form. We do not touch it. And in the second expression, when we know that the first component cancels, and we need to put the second component. So, but you see, what you have here is that the second equation in digital form will have this structure. So it's 1, 2, 3, 4, 5. 10 power 5 x1. Five, but these numbers we cannot they are beyond our accuracy. Our accuracy is that we should truncate it after the third number. So you see that actually the second the computed equation will be, this is 2, no? 2 will be of this form, which gives you the solution to be exactly 1. So which is okay, because x2x is really close to 1. But then you need to use the first equation for the computation of the rest. So whenever you substitute it into the first equation, you have to compute x. So what do we have? So we have to compute it as x2, x1. No, x1, yes. It should be just same formula appears, right? So it's 10 power 4, which is 0.1, 10 power 5, x2 minus 1. But x2 is 1, so it's 0. So it's wrong. So you see we're missing just one digit. We kept 4 digits and we got completely wrong result. Instead of 0, instead of 1, we got 0, because it must be 1. So that's an idea. So that's what is what I thought as a second reason of error. So the first, there were two types of errors. One was a rounding error. The ones that we cannot avoid at all, so we're always making operation we have to round, because we have finite number of digits. But there are also method error. And this is a method error. So we use the method which is very sensitive to rounding for this particular problem. And there is a solution. So the usual solution for this problem is that it's called pivoting. So whenever you use Gaussian elimination method, remember that you take one of the values and try to eliminate all others, to put in all of them to 0. So you eliminate by subtracting, eliminate the others. Then you take 0, the other element, and you eliminate the others, and so on until you get the upper triangular matrix. So the idea is that, so these are pivots. So idea is that you always use the largest element of the column. You cannot just blindly take the first, even if it's not 0. So we took it blindly first, but it is very small. You see? So you should take the one which is bigger. So if you start with 1, so this is a good exercise for you that check that it works. It works for this problem. So if instead of taking just the first, you take the one which has the biggest coefficient, you will be safe. So you will not make this large problem, large errors. So this is that's why taking care of this round of errors in a method is important. And usually, many problems in numerical analysis they're usually two sides. So one is to avoid errors. Another side is to optimize the performance, so to make everything with less operations, to make everything faster. So there is a concept which is related with this method error, which you can consider in the following way. So the functional evaluation. So whatever method that you use, you have some input data and you want to compute the result. So essentially, you compute functions. So what you do with essentially any algorithm, you compute some result of some function of some input variables. And so we can just make our definition about the function. So let's consider a function, f of x. Okay, and it can be a vector or it can be have values in discrete set, doesn't matter. So let's just make it for the usual real function because it's essentially all definitions are similar. So, and let us assume that it's continuously differentiable. So it's continuously differentiable. So what do we have? So the function, so we can write Taylor series. Near some given point. So the idea is that we want to, x star is the point where we want to compute the function. And x is a point when we, in fact, computed the function. So what is an arrow? So the arrow can be estimated just by Taylor series. So it's function at that value plus derivative of that value by the difference. I think star is everywhere above. Okay. And then we can compute that the relative arrow. So what is a relative error? A relative error is a difference of the results divided by the function, by the value of the function. At the point where we want it. So the relative error of the computation will be, we just put it in. So so you see, it's for real functions, but if it's vector, you put a norm, or whatever space you want, you put a norm instead of modulus. And then you substitute this by this expression, and this will be f prime of x star by x minus x star. But then I want to do and divide it by modulo of x star. Everything is a modulus. And then what I want to do, I want to divide it by x star. So I have to multiply this by x star. Okay. And you see, so this is relative error of the result, and this is a relative error of the input. So if you cannot, well, in most cases, you want to compute the value at x star, but you can only have x, which is different for some reasons, for the reason of round off, for example. So if you know what is your relative error for the input, for example, if it's round off, remember that the relative error is this unit round off value, and then you know what will be the relative error of the result, and they're related by just a coefficient which is called condition number. So this is how comes the condition number. I think I'll put it here. So definition. So the condition number of function f of x at point x star is, so this is condition number of function f at the point x star is this modulus of x star f x star prime divided by f x star. So the condition number is an amplification factor. So condition number, when you function amplification, it's amplification means that you gave as an input some data with certain error. How many times the error increased after you, in relative sense, after you made the computation. So you can see in this example, the error increased 100%, right? So this is condition number will be. So it's actually condition number. Let's make the computation. So the condition number is the increase. Is the increase of your error, which you can a priori compute knowing the function. Okay. Yeah, and this condition number for this example was huge because what happened is that we had very small error in the data because our error in the data was to cancel the fourth digits, the fifth digits. So it was the error is this. So it's very small, and the result was 1, and the error of the result was about 1. So you see that condition number of this computation for this example will be something like 1,000. So the large condition number means that computation is ill-conditioned. So this is what people say, ill-conditioned. So whenever you say that some computation is ill-conditioned, and there are many problems which are ill-conditioned by itself. For example, in linear algebra, computing Jordan normal form is very ill-conditioned. So it means that if the problem is ill-conditioned, you can solve it, but it signals very bad thing. It means that if you make a small mistake in the data, it will be a very, very large mistake in the result. So you should be ready for this. And there are very simple, you can put very simple examples to see it. So for example, if you take square root of x, right? So what is the condition number? Condition number is x, f prime will be 1/2 square root. And then you divide by f, right? So this will be 1/2, no? 1/2. So it's well conditioned. So having error in x, you don't expect big error in the computation of f. And another function, which would be x minus 2. The condition number will be x 1/2 minus 2 over minus 2 x divided by, so it's so this is infinite for x equal 2. Right? So this is mean that it's ill-conditioned for x close to 2. So whenever you have x very close to 2, the error of the function will be much larger than the error of x. Well, and this is, which is rather natural in this case, because square root is, essentially this has to do with divergence because of the non-differentiability. Okay, so I think this is it. This is it. And the next big topic is the integral computations. Not a big topic. This next topic, which I still hope to finish today. By the way, before going to the topic, you will have exercises, and also including these programming exercises. So there is a monitor. There is a monitor whose name is André. Consider. So André, and he will, let me see if I can give you his email. He has an email from, well, he uses his email from UF. So it's André. Consider ID. But he will send email to everybody who is registered on the web. So if you register, he will send you an email, because he will send it to everyone. But if you are not registered, you can send him email yourself. So I expect that he will have, well, first of all, he will be responsible for the exercises, and also with Andrei, you will be solving the problems. And I think that there will be also a special date during the week when you can talk to him. Okay, so let's consider. Here's a monitor. Okay, so the next topic is integral computations. So the integral computations is not very much used form of computations, but it is interesting for several reasons. One of the reasons is it's interesting for pure mathematics, because it's a way how it's becoming a rather popular way in the recent decades how you prove theorems with a computer. So there are many problems, like in number theory. I know several several in dynamical systems, like computation of this Feigenbaum function and proof of the existence of attractor for the Lorentz system. So there are several theorems which technically, which are very important for the field, but technically they are extremely hard to prove. At the same time, you can make a program which make a certain operations that you prove that are exact, right? So they prove, so the all operations that the program is doing is rigorous, and you can prove that depending on the result what program gives you, your statement is wrong or is correct or wrong. So you can make a computer assisted proof. This is a rather big trend already. So what does it mean? It means that we need to have mathematically rigorous computations. And in this case, it's actually mathematical rigorous bounds. Of exact result. And the result, it can be some estimation of the function or some estimation of a number and so on. But important is mathematically rigorous. So this is what we did not have before because of, for example, of these kind of examples. So you can take 3 digits, a result is wrong. You can take maybe 20 digits result. You can still cook the example where the result will be wrong. So we're not sure that the result is correct, but kind of we're almost sure. We can put more and more digits and see that everything works, but we don't have a guarantee that the result is correct. So with interval computation, we do have this guarantee. So essentially, the interval computation has to do with computation which is not a number, but with an interval. So what you have is that the number, so the object of the computation, interval computation is an interval. So now whenever, in interval computation, whenever you write x, it implies that it's not a number, but it's upper and lower bound. So it's a couple of values. It's 2 values, so when you give x, it means that you're giving interval for the lower and upper number. And then you have to make operations. You have defined operations. So the operations, so in that case, this is a rigorous representation of a number, of any real number, in the sense that all it means that the whatever value you're interested in will be strictly inside this interval. So this is certainly you can do with finite number of digits. So you can give an interval where your value is, and this interval can be as small as you wish if you take more and more digits. So this can be very precise, and it's important that it's rigorous. So now we can write operations. So we have, imagine we have 2 numbers, 2 intervals. So how you define operations? And that's very elementary. So sum of the 2 intervals, what it is, so it's if you take 2 intervals, then the result of the sum lies between the sum of the lower bounds and upper bounds. Okay, so that's elementary. Then the difference. So this is, you should put it way around, right? So it's minus upper bound and then upper bound minus lower bound. Okay. It's very simple. So x product of the two will be between minimum, and here you list all the products that you can have. So just check that it's true. X, y, x, y, x, y, x, y. And maximum of the same. So if you have two intervals, the product will be in the interval between the two limiting points. And then if you want to divide, this is a bit more tricky. So now when you divide, the problem is that is about 0. So if there is a 0 inside or not. So if there is no 0 inside, so if 0 is not inside this interval, then you can define the inverse of the number as just inverse of the bounds in just in opposite direction, right? And then you can divide y by x, so it will be. You can just reduce it to the previous operations. It will be 1 over x times y, which we already defined. So that's elementary operations, and we can try to see. So example is, let's take x, which will be minus 2. We computed x, we know it between minus 2, and let's compute the function plus 1, x minus 1. Okay. So what it is? So you just substitute it into the formula. This is a exact interval, so you just add it inside. And now you use this expression, so the smallest will be minus 9, right? And the largest will be 3, I think. Yeah. So we computed that whenever x is here, then the result of f is rigorously inside this interval. So this is the idea. And of course, this is putting 0 inside interval. It's also not a big problem, because then you can you can also include division by 0 using extra numbers, which is plus and minus infinity. So if you add plus and minus infinity in your vocabulary of the numbers, then you can also include you can relax this condition. So there will be intervals which you obtain when you divide by 0. Okay, so that's how it works, and also we know that this is how it works analytically, and we know that we always we have a round of errors. So the observation is how to deal with round of errors. So what you do, you make rigorous enclosures. So what does it mean? So it means, for example, you want to add to intervals. So this is an operation, and this is an operation where you have round of error, so which means that you always have to make some truncation, or either chopping or rounding or whatever. So how you do this rounding such that you are obtaining the rigorous result is that for the first you should downward rounding. So when you truncate, you always truncate to a number which is smaller. And the same when you truncate or round this number. So when there are some digits that you have to forget, that you have to round it always to the larger side. So the result due to the round of error will be slightly bigger. And if it's slightly bigger, it contains rigorously the correct interval. So that means that the result is rigorously correct. It will be upward rounding. Let's do a small interval break. Coffee. Okay. So the next step, what we want to see is actually rather simple but not completely intuitive fact that another property, another observation is that actually when you do the computation with intervals, right? So the result depends on the order of the operations. For example, if you take product first sum and then product, or you take two products, they are not generally the same. Not generally the same, but in fact, they are. So the first is the subset of the second. So generally not equal. So this is what's called subdistributive. Property. So operations, again, numerical analysis is violating some of the basic properties of algebra. And actually, we can see something like this exactly on this example. So on the let's compute that f of x, but opening the parentheses. So it will be x squared minus 1. And that will be minus 2 squared minus 1. Now you can define make a definition of what is x squared, right? So you can define x squared depending on the, given an interval, define what is x squared. So this you can do. So you can make it as an exercise. We'll look at in the book. But clearly that x squared will be from 0. So you can make it in such a way which is giving you just exact interval for the result, which will, in that case, will be from 0 to 4. Yeah, it will depend which is smaller, which is bigger, which is negative, which is positive, and so on. So you can make an explicit definition of x squared minus 1, and this will be minus 1, 3. So you see that you get a different result from what we had before. So we just used a different expression. So instead of product of sums, we took difference of products. And we got different value. But certainly this value is more precise, yeah? Because this is a subset of what we had before. And this is exact. This is exact in the sense that if x belongs to this interval, so taking different x from this interval, we can obtain any number in this interval. So this is the exact relation. So it means that if we take interval as an input, this is exact interval as an output. And this is not exact. So depending on how you compute, you can get exact result in terms of interval arithmetic, or you can get a result which is still correct, but it's correct in the sense that it will contain the exact result. And there is a theorem about this. There is a theorem which is essentially tells you what to do with interval arithmetic. What is a better strategy? Essentially, all your computations with the arithmetics is based on this theorem, ideologically. So fundamental theorem of interval arithmetics. Good. So what it tells? So let us consider the function. So function means our algebraic expression. So f of certain. So all arguments are intervals. So now everything is interval, and value is interval. So this is a function or algebraic expression. So it'd be so in other words, it's your algorithm or some computer program which is given these inputs, compute some output with different using these algebraic expressions that we defined. So evaluated. So we evaluated with interval arithmetic based on 4 elementary operations. So that elementary operation is plus, minus, multiply, or divide. And some incorporated functions that you can make extra by hand. So like the function that we discussed, the x squared. So like x in any power n. You can also define cosine x. You can define exponent s, x, and so on. So you can, in the sense that you can write special programs which evaluate some elementary functions. Just give an interval, it gives you the interval for the result. So the version related with information based on point. Then what we have? So first is that the interval value that you obtain contains the exact range of f over the box x1 xn. So what it means that you see each variable x1 xn is an interval. And then we have n of them, so it's n-dimensional space, which means that each one is an interval. So we have something like a box in each direction. It's x1, x2, x3. So this is a box which corresponds to is given by these intervals. And we guarantee that whatever interval we obtain for f with this computation, so it will contain, so any point inside the box will be inside this interval. So that's important property. So we give intervals for each variable, so it gives you some volume, so the box. So whatever value we have in the box, it will be sent by f to some point here. So usually for the examples we see by hand, this interval is big, so it's not surprising. But the power of this method is that since you have big computers, large memory, so you can actually control very precisely the value of any real function by using small boxes. So this is essentially the idea, and this is rigorous. So we know that whatever doesn't matter where inside the box we are, the value is certainly in this interval. So that's the first part. And the second part is about how accurate it is. Actually, there will be two theorems about how accurate. The first is has to do directly with this difference between the computation in one way or the other way. So this is the second part of the, so this was one. So now we will have second part of the theorem, which tells that if single functions, single variable functions, this xn, cosine x, and so on, return and elementary operations. Return exact results. So it's just assuming that everything is computed with an interval arithmetic exactly, so forgetting about round-off errors. Then what is the optimal way how to compute a function? Yeah, so what will give the smallest interval? So, and this is given by the second condition. So if the end what? And if each variable from this set occurs only once, but at most once. So, in principle, it may not occur in the expression. Of f. Then the value of f obtained by interval of arithmetics, by interval with arithmetic yields the exact range of f over the box. So what does it mean? It means the following. So the first part tells that whatever point we take, it will be in the interval which will be returned by your function. So the second part tells you that if in all these operations every variable just appears once, then it will be the exact range. So it will be the exact range, so there will be no, so every point inside will be in the interval, but also every point in the interval will be obtained from some point of the box. Right? So it means that in this case, the computation is best possible. So for having the correct precise computation with intervals, your expression should contain only once every variable. And you can see it very clearly here. So if we compute these functions in this way, x appeared twice. So first it appeared here, then it appears here, then we made the product. And if we compute with this expression, x only appears once. And that's why this was an exact result, and this was still correct because it still contains the range, but it will be much less accurate. So that's essentially the idea. So we can think about how to prove it. It's actually rather elementary, but just try to think how you justify these two things, these two statements. And the last property in the integral arithmetics which we address is actually accuracy. Okay, so let's write the so just repeat. So if f contains some variable, I'll just write it down. So if f contains some variables more than once, then overestimation can occur. So this overestimation that we had with the example that I just erased. And this is, there is a word for, there is a concept, name for it, it's interval dependency. So if variables appear more than once, which is in most cases usually the case, you have this interval dependency, so you are not optimal in computing the result, which means that your result will be worse than it could be. So what to do? So what to do is to use the power of the computer, and essentially the next theorem tells you that there is a general rule that the smaller the intervals, when you use smaller intervals, because with a computer you can always try to discretize with the smaller regions. So smaller the intervals gives you the smaller interval dependency. So overestimation becomes smaller the intervals that you use from the beginning, and this can be formulated exactly as a theorem. So let's put a definition. So the definition first. So suppose that your algorithm gives the result, the interval AB. And also, but the exact range, of the function f, which means that computation of all values all exactly. So x star is exact number which is in the interval. For all I. So suppose the exact range for these intervals, for these variables, is some other interval, CD. Well, of course, so what happens? So we have this value. So we have the exact interval CD, which is range. And your algorithm gives you some interval which certainly contains CD because we're with exact arithmetic. We have a rigorous estimation, but it can be bigger. So there is an excess. So this is exact range. And there is an excess. It are the two intervals between A and C and D and B. So then this is exactly what we want to so we define the excess as, so the excess of the function f at given intervals is defined as the size of these extra intervals which are where the value just cannot be. So it will be C minus A plus B minus D. So this is a value which gives you how bad, so it is very big, so it gives you how bad is your algorithm compared to the best possible way. So the best possible is that way when you get exact range of the function, and your algorithm probably cannot do it. It gives you bigger interval, so the excess is exactly the measure for how big is it. So the theorem, the second theorem, which is exactly about about how to make your method good, working good. So excess of the function over the and values at the order of magnitude is big O of a maximum from all the widths of all intervals. So here where width is just is a width, so size of the interval. So remember what it is. So recall what it is. So recall that if you have some function indexed by k and some estimating quantity also indexed by k, so we say that f of k is O of alpha k if the limit k goes to infinity is bounded. Oh. I think like this. So essentially, so if the ratios are bounded, yeah. So that's correct, no? Correct. So anyway, what theorem tells you is that the excess has this order of magnitude of the maximum width of the width of the maximum interval. So use small intervals, you get small excess. So it doesn't matter what is your algorithm. If you fix algorithm, okay, it is not. It has interval dependency, so it gives you not so good results. So the result is worse than the exact range. The result is worse because you cannot just use every variable once. Maybe you have to use it 1,000 times, so you cannot avoid it. But it doesn't matter. If you have good computer and you can use very small intervals, then you can that excess can also be small. Just use small intervals, and by order of magnitude, your excess will be estimated by the largest interval that you use. That's it. So I think that we're done with this topic of the error, essentially of the elementary computations. I will stop today here. So everything what I told you is essentially the first chapter of that book that I mentioned. Classical and modern numerical analysis. So you can just go through and see. Maybe you're interested in some other aspects, but you will have exercises. So now we move to the next topic, and we will already start analyzing something more complicated. But this is, despite it, this is elementary, but this is very important to understand, because this, all these ideas about errors of the method are important. So usually in your practice, you don't remember about this until some problem occurs. And then when a problem occurs, you start thinking, what is the trouble? And sometimes you find out that, okay, the trouble is because you round off after tens digits, and this is not enough. Or you subtracted one big number from another very close big number, and your error exploded. So all these things become important, may be important. So just some very slight changes in an algorithm may dramatically improve your method. So that's why it's good to know, just have an idea of what happens with an error. Already okay, I think that's it. I think we finished a bit earlier today, because I will not pass. Better to start.